So I'm going to talk now about, I would say, my main PhD project that I did in Munich, together with Singzap, Gabi, and Jan. And if you want to know more, it's written up in these two publications here. My current talk will mostly be about this recently published PRL. So what we did there is we investigated quantum criticality in Heavy-Fermion systems by studying the periodic Anderson model using cellular dynamical mean field theory together with a numerical renormalization group. And what we found is a phase diagram that's quite paradigmatic. So it features two Fermi-liquid phases with different Fermi surface volumes separated by a so-called Kondo breakdown quantum critical point. And what the numerical renormalization group allowed us to do is really study the quantum critical fan, where we find strange metal behavior, and this will be the main topic of my talk. And so things that we found is omega over t scaling, Planckian dissipation, a linear T resistivity, and what I really want to emphasize later is the importance of vertex contributions to this linear T resistivity. Good. Oops. Okay. So let me start with heavy fermions. So the basic ingredients that we kind of need to model heavy fermions is, or to have heavy fermions is we need some elements that contribute localized f orbitals that then hybridize with other itinerant conduction bands in these materials. So examples would be ytterbium, rhodium to silicon 2 or the 115s here. And on a very basic level, we can model that with a periodic Anderson model, where we have just a single itinerant conduction band that's non-interacting and a completely localized f orbital that with a large on-site interaction and local hybridization to the conduction electrons. And basic level, what we can then obtain when we tune this hybridization, for instance, is if the hybridization is large, we will generate strong CF entanglement, form collective Kondo singlets, and that will lead to quasi-particles that are kind of hybrid CF objects with a very large effective mass, and importantly, the Fermi surface counts both C and the F density. Then on the other hand, we can have RKQY correlations, and if the hybridization is low, these can actually take over. The F moments form some sort of spin liquid and are approximately at low energies and temperatures decoupled from the F. The conduction electrons are decoupled from the F moments. And that leads to a small Fermi surface that only counts the C electrons. And these two scenarios are separated by a quantum critical point that's called Kondo breakdown quantum critical point. And indeed, in experiments in the quantum critical region, we find very clean, strange metal behavior that's similar also to what is found in cuprates right up above the superconducting dome. Right. Now, this would be an example. So ytterbium, rhodium to silicon 2, where this is very nicely seen. And the nice thing about heavy fermions is that you can actually tune them very easily. So ytterbium, rhodium to silicon 2 is, for instance, can be tuned through the quantum critical point by a magnetic field. So the blue regions here where the resistivity goes as T squared, these would be Fermi liquid regions. So here with a large and a small Fermi surface. And one of the early measurements that indicated a Fermi surface reconstruction there were Hall coefficient measurements by Silke Paschen. And if you extrapolate the Hall coefficient to low temperatures, as you tune across this quantum critical point, it seems to extrapolate to a jump, suggesting that there is something dramatic happening to the Fermi surface. right? And in this orange region here, the temperature is linear in T, as measured here. And for instance, what you also see is omega over T scaling of the optical conductivity and also other quantities, log T specific heat coefficient. And yeah, it seems that there's no notion of quasi-particles there. Right. Now we studied this, or tried to study this numerically by studying the Perdig-Anderson model. And we studied the Perdig-Anderson model in 3D on a 3D cubic lattice. So this is kind of just a toy model. And so our parameters are basically chosen such that the half bandwidth of the conduction electrons is 1. The local F-electron interaction is 10 times as large, and everything is tuned such that the C electron filling is about 1.3, and the F electrons are approximately half filled, okay, so that they actually form local moments. And what we control in the end, so our control parameters are the hybridization and the temperature. We studied this in cellular dynamical mean field theory, so not single-site DMFT, because we need to kind of capture this competition between non-local RKQY interactions and the Kondo screening. And the two-side cluster is essentially the smallest unit where you can see this kind of competition. I should also say that we purposefully exclude symmetry breaking. I mean, we wanted to really study this Fermi surface reconstruction in the absence of some symmetry breaking. So we didn't want kind of some magnetic order or so to actually reconstruct the Fermi surface. Right. Now, cellular DMFT, opposed to single-site DMFT, has some momentum dependence of the self-energy. And however, in a very, it has a very coarse-grained momentum dependence of the self-energy. So in the two-side version, we have kind of one cluster momentum eigenvalue that takes care of the entire gamma point. So, or not the gamma point, but the region around the gamma point. And another cluster eigenvalue basically that takes care of a region around the pi point. Okay. Right. Now, since we want to study quantum criticality, and this is all going to take place at very low temperatures and very tiny energy scales, we need an impurity solver to actually be able to give us this low temperature and low energy resolution. And for that, we use the Numerical Renormalization Group. And that also gives us real frequency dynamics, so we don't have to go through any analytic continuation or so, which is pretty nice. Good. Now, this would be the phase diagram that we find. So it's so the tuning parameters, as I said, is the hybridization and the temperature. And now at low temperature, so the temperature is on log axis, what we find is, on the one hand, if the hybridization is large, we find a Kondo phase with a large Fermi surface. So what this actually is this is kind of an electron pocket on top of a completely filled band. So there's an entire Brillouin zone volume actually missing in this picture. Okay. On the other hand, if the hybridization is small, we find a small Fermi surface. So this is what it looks like. It's consistent with the bare conduction electron Fermi surface, and also a Luttinger surface, which in our case takes care of the missing Fermi surface volume, though I'm actually starting to think that this is more like a coincidence. Right. And in between the Fermi surface jumps, this is basically happens at this Kondo breakdown, Kondo critical point. And you can also see that we have this orange Kondo critical region here, where we find no quasi-particles in the NT dependence of the resistivity and omega over T scaling. And I'm going to now talk mainly about that. Right. So now to investigate scaling and the physics in this quantum critical region, I'm going to actually focus on the temperature dependence along this red line here. And so the reason is that we have the largest scaling, right? So the largest extent in scaling basically on this line. Okay, so it's our closest point to the quantum critical point. And the first thing I want to show you is how we actually extract these energy scales here, or temperature scales. So we do this by looking at fluctuations on our cluster. So basically look at spectra of dynamical susceptibilities. And these spectra kind of fall into two basic classes here, kind of represented by two representatives. So the total F magnetization, the staggered F magnetization. And the corresponding spectra are shown down here, right? So it's a function of omega and spectral weight. So on a log-log scale here at 0 temperature. And what you can see is that they really behave quite differently. So the total F magnetization has a maximum at the non-Fermi-liquid scale. This is also in many cases also called the coherence scale in heavy fermions, and then goes linear in omega. So actually these total magnetization fluctuations are screened at this scale. While the staggered magnetization actually then develops this plateau and is only linear in omega below the Fermi-liquid scale. Okay, so what that basically means is that we have some two-stage screening going on here. Right. And another point I would like to just quickly mention is, I mean, we basically see the Fermi-liquid scale vanishing continuously, and also all the, right, so there's basically nothing, except for the Fermi surface, there's nothing discontinuous across this quantum critical point, meaning that this is actually a second order transition. Right. And now I want to actually show you the temperature dependence that you get when you cool down. So the temperature dependence for the staggered F magnetization susceptibility. So this is shown here. I mean, it's of course not all the data yet. So up here you can see the temperature, and up to now this is basically just the two high temperature curves. And down here you can actually see the corresponding real part. Now if we cool down, you can see this plateau here emerging, while in the real part there's a log omega dependence that grows, right? And below the Fermi-liquid scale, essentially all the temperature dependence is gone. Right. Now, it turns out if we plot the spectrum as a function of omega over t, we actually get a very nice scaling collapse in the non-Fermi-liquid region. So you can actually see that these orange to green curves here nicely lie on a single curve. Of course, at some point mean they then bend away from it. If we go out of the non-Fermi-liquid window, that means we have omega over t scaling of the staggered spin susceptibility. So for the real part, we have to actually subtract divergent logarithmic contribution of the static susceptibility. And if we do that, we also get logarithmic omega over t scaling. Now we can make a scaling ansatz to extract some decay rates here, actually. So what the scaling ansatz essentially is it essentially fits the spectrum with a superposition of Gaussians. So basically we have some mean energy and some decay rate. And what we then fit is the decay rate and the mean energy. And the main point is basically that the decay rate, so the coefficient of the decay rate, so which we make an ansatz b times t, right? And this b coefficient is somewhere between 1 and 2. So it's on the order of 1, meaning that we have Planck anticipation there. And now these black dashed lines here, this would actually be the fit. So so in the end, this is all one scaling function, right? And you can see that it actually fits pretty nicely up to the gray error bars, right? Okay, now let me come to the optical conductivity. So this is now going to be the main part of my talk. And the main message I want to actually send. So first of all, I mean, the optical conductivity, for what we have to do is to compute this, we have to actually compute the uniform current susceptibility, okay? And this is quite challenging in cellular DMFT because now, opposed to single-site DMFT, we actually have vertex contributions to this current susceptibility because our self-energy is not strictly local anymore, okay? Also, what we can do is we can actually compute the local current susceptibility. What we find, so this basically amounts to just defining a local current operator on our bond that's on the cluster, okay? And we find that this actually exhibits omega over t scaling in a similar form as the staggered spin susceptibility. Okay, so meaning that actually there are some critical current fluctuations in this non-Fermi liquid region, right? Turns out that, however, these critical current fluctuations are actually not captured by just the bubble contribution. So that would be the thing that basically contributes in, for instance, single-site DMFT, right? But what we can do is, so to kind of approximate this bubble contribution plus vertex contributions, okay? What we did is essentially we approximated this by the uniform bubble contribution, which we can very easily compute from the Green's functions, right? So it's just a convolution of two Green's functions. And the vertex contribution is approximated by the local contribution, okay? So we basically neglect all the next nearest neighbor, next nearest neighbor, etc. So all these non-local contributions to this uniform vertex contribution we completely neglect, okay? Right. And when we do this, this is what we get for the optical conductivity. So this is now again on a log-log plot versus different temperatures. You can basically see that so if we start out at high frequencies, right? So there's kind of this dip forming here. So this is known as hybridization gap in the optical conductivity, and then it actually rises as 1 over omega, and finally at the lowest temperatures and frequencies, it just converts into Drude behavior, okay? Which is of course expected. Now the first thing that we can do is we can again plot it as a function of omega over t. We have to, however, multiply this by the optical conductivity by temperature to achieve some scaling. And you can see that we actually find very nice scaling behavior. Again, we make a phenomenological ansatz, which is this dashed line here. And that also tells us that this is the current fluctuations have a decay at a Planckian rate. And one of the nice things is really that this has also been measured in ytterbium rhodium 2 silicon 2. Unfortunately, only this region here has been measured, right? And I mean, you can see that there's quite some similarity, right? So there's also this 1 over omega slope here in ytterbium rhodium 2 silicon 2. And the power here is also 1, right? What would, of course, be nice is to, at some point, actually see the low frequency and bend over of the scaling function. Right. What the scaling also implies is essentially that we have a linear T resistivity, basically by just evaluating this at omega over t equals 0, right? The resistivity is linear in T. And we also computed this, so you can actually see that above the non-Fermi liquid scale, the resistivity rises, goes through a maximum, and then drops first linear in temperature and then crosses over to a T-square behavior below the Fermi-liquid scale. Right. And I think what's also worth mentioning is that the imaginary part of the optical conductivity also shows omega over T scaling. Right. Now, of course, we have this very nice data, and I've also told you that we are kind of incorporating vertex contributions from the local part, okay? And what I want to show you now is that these vertex contributions are really important in the non-Fermi liquid region, okay? So they're almost, so at least the local ones are almost negligible in the in the Fermi liquid and above the non-Fermi liquid scale, but between the Fermi liquid and non-Fermi liquid scales, they're really important. And to do that, I want to actually dive a bit into the single particle decay rates and quasi-particle weight and quasi-particle decay rate, because those quantities actually determine the bubble contribution, okay? Or it's not quite correct. So the single particle decay rate controls the bubble contribution, while the quasi-particle weight and the quasi-particle decay rate actually don't. So they actually control how the single particle, so how the Lorentzian line shape in the single particle spectrum, so in the single particle spectral function actually looks like. Okay, so especially the quasi-particle decay rate tells you how the width of the spectrum of the Lorentzian line in the single particle spectrum. Right. So now this is what we get for the single particle decay rate, and as you can see, is that the single particle decay rate is actually log t. Okay, so it's not linear in t. Which actually means that the bubble contribution that we would get in the non-Fermi liquid region would actually also have some log t behavior, okay? And then only below the Fermi liquid scale, it goes t square. If you look at the quasi-particle weight, that quasi-particle weight is actually linear in temperature, as it turns out. So it starts, right, so it starts out at some large value, then drops quite significantly across the non-Fermi liquid region, and then in the Fermi liquid it goes constant, as you would expect, right? So the quasi-particle weight should better be constant in the Fermi liquid. And now if you put the two together, so we multiply them, we get the quasi-particle decay rate, and as you can see, the quasi-particle decay rate is actually then t log t. Okay, in the non-Fermi liquid region, and of course t square in the Fermi liquid. What is quite interesting about this is that the quasi-particle decay rate is actually the same as what you would expect from a marginal Fermi liquid, but the roles of the single particle decay rate, so this bluish line and the green line, so they are actually interchanged. So a marginal Fermi liquid would have a log t quasi-particle weight and a linear in t decay rate, and this is interchanged here. What that means for us is that the bubble contribution actually does not show linear in t behavior. Okay, it doesn't really show strange metal behavior, the bubble contribution alone. And this is kind of shown here, where I again show you the optical conductivity. So this is frequency and right, and the spectral weight. This is essentially the same plot as from the previous figure, but I've included the bubble contribution at the lowest temperature. Okay, so this would be the gray dashed line. And what you can see is that at high frequencies, it actually matches quite nicely. So there's not that much vertex contributions there or vertex corrections, while it also captures the low frequency Drude peak in the Fermi liquid. But in the non-Fermi liquid region, you can actually see that it goes completely wrong. Okay, so there are extremely strong vertex contributions that come only from this local vertex correction that we do, right? So what I can kind of conclude from that is that we really have a strange metal from vertex contributions and not due to a single particle decay rate. Okay, so this would be really the main message from my talk. So for instance, if you do some cluster DMFT or so and you don't see a linear NT decay rate of a single particle decay rate, might still be that this could actually still be a strange metal if you actually included some vertex corrections. Okay, right. And now for the rest of my talk, I want to go a little bit into analyzing the transport scattering rate and the optical mass. So they're defined basically by writing the optical conductivity in this form here. Okay. And what's also, of course, interesting is the static scattering rate, which is essentially proportional to the resistivity, the static mass, and the renormalized scattering rate. Okay, also because these have been looked at in experiments, right? Okay. So first of all, this is the data that we get if we do this analysis, and you can basically see that the transport scattering rate has this maximum here. Okay, so this is where the hybridization gap was before. So we have very strong scattering. And so Antoine, do you have a question?
Yes, actually I do. So when you use this sort of extended through the parametrization of sigma of omega, right? I'm a little uncomfortable about the one in the numerator. There is actually a plasma frequency there, right? And so
yeah.
how you exactly, it's an agnostic parametrization because you've allowed for omega and t dependence of tau and m star, but we still have to negotiate what you're going to put it as a plasma frequency. And, in optical conductivity of cuprates, what you put there plays a very important role. So how do you do it?
Right. So the plasma frequency in my definition is actually absorbed into the tau. So we didn't make an effort to actually, right.
I see. So you really fit things with one, and I should understand tau and m stars.
Yes, right. So the
having plasma frequency hidden in them. Okay.
But it's hidden in there, right? Yeah.
Okay, thanks.
Right. And then you can basically see it drop, right? So the as a function of omega and then go as basically omega square here, right? So one of the things that's kind of interesting is so if we actually look at the deviation from from tau 0, can actually see at the lowest frequencies, even in the non-Fermi liquid, there's an omega square behavior. And this omega square behavior is essentially when the scaling form crosses over to this flat plateau. Okay, though with a coefficient that goes as 1/t in the non-Fermi liquid, opposed to a Fermi liquid where this would actually be constant. Right, and now the optical mass. So you can see that the optical mass actually is negative at high frequencies and then saturates to some constant value. And turns out that this optical mass is actually seems to be quite well defined in the non-Fermi liquid. So there seems to be some well-defined optical mass, okay? And what's important is that this optical mass is quite different from the optical mass in the Fermi liquid, okay? So this is again a log scale here. You can see that it actually shoots up by several orders of magnitude once we go into the Fermi liquid and then settles to that value, right? And what's also quite interesting is the renormalized scattering rate. So first of all, the renormalized scattering rate is linear in t, and what we also observe is we actually observe some t-square behavior in the crossover region. So basically right below t non-Fermi liquid, it first does some shows some T-square behavior before it really goes linear in T deep in the non-Fermi liquid. And that's interesting because it, so this is interesting because something similar has actually been observed in cerium, cobalt, indium 5. So in this recently published PRB here. So these are measurements, okay, on the material. As you can basically see, again, this is there's this peak here, and then it goes, the resistivity goes linear in T, while the renormalized scattering rate goes as T square, and the optical mass actually rises. And the interesting thing is, so what the authors kind of here conjectured is that there is some hidden Fermi liquid physics going on. However, if we compare that to our data, so this is now on a linear scale, so everything I showed you before was on log scale, you can actually see that we also find T-square behavior of this renormalized scattering rate, so it actually looks pretty similar, at least qualitatively. We also see the optical mass rising here, and also the resistivity looks very similar, right? Good. And now, on my last slide, I want to also quickly mention, talk a little bit about specific heat and entropy. So since we are using NRG as an impurity solver, we can actually very nicely extract entropies and therefore also extract specific heats. And one of the hallmarks of Kondo breakdown behavior, of the non-Fermi liquid behavior across above a Kondo breakdown, Kondo critical point, is that it has this log T dependence, and then crosses kind of over to power law behavior. And that's something that we also find, right? So this is, of course, now a log linear plot, and this is a log-log plot, but these dashed lines here show log T dependence, and then we basically find this power law behavior, and of course constant specific heat coefficient in the Fermi liquid. Okay, right. And with that, I want to conclude my talk, and I hope you have interesting questions and can have some discussion. Thanks for listening.
Right. Are there any questions in the audience? Antoine?
Yes. Thank you very much, Andreas. Very stimulating. I would like to understand a little bit better what you think is the nature of this non-Fermi liquid fixed point. You had a slide where you analyze chi of omega and T in terms of some power law, chi double prime. Can you show that again?
Sorry. You mean this?
There was something with an integral epsilon over T to the nu somewhere. Not this one.
This one, right?
Yeah. So I would like to understand this a little bit better. What's the exponent nu here? Where does it come from?
Right. So the exponent nu is kind of a fit parameter
to the data.
Right, to the data, and it comes out roughly 0. So
okay.
That exponent kind of fits as the slope of the plateau, actually.
I see. So basically, this is telling me that your numerical data are consistent with chi double prime being omega over T for omega smaller than T and then constant, essentially.
Right, yeah. So it basically tells you that the scaling function is constant if omega is larger than T, right? So for omega with larger than 1. Yeah.
I see. And do you have any insight in some analytical, from NRG insight in the nature of that non-Fermi liquid fixed point? Can you relate to any?
Right. So so the first thing is it's actually a bit tricky because so one of the issues is that first of all the hybridization function is quite frequency dependent. Okay, and that frequency dependence seems to be important. Now,
Is it singular at low energy?
it seems to actually become singular. At least the derivative seems to become singular as you extrapolate to the critical point, right? So it seems to actually become singular at the Fermi surface. Yes. Of course, I mean, so the generic scaling and also the log t dependence of the specific heat coefficient. I mean, from that it seems very suggestive that this is kind of in the two impurity Kondo or two impurity or two channel Kondo universality class kind of, right? Though the two impurity Kondo model, I mean, it's is unstable to particle Hole symmetry breaking that we have here, right? So we actually checked whether the finite size spectra are consistent with kind of some restoration of particle Hole symmetry, though that doesn't seem to be the case. So the finite size spectra actually seem in the non-Fermi liquid region actually seem to have particle hole asymmetry. That's inconsistent with the two impurity fixed point.
But so if you have a singular delta at low energy, it also means that it's not the run-of-the-mill two-channel and perhaps even CFT approach.
Yes, right.
It's more difficult than what you would usually do.
Right, precisely. So that's kind of the problem that, I mean, we cannot approximate it by a flat density of states, right? Yeah.
Okay.
Right.
Okay, very interesting. Thank you. So it's still an open problem, basically, what the nature
It is, right. It is kind of still an open problem. I mean, maybe what I can also say is that it seems to me that so that kind of two-particle scattering between the bonding and anti-bonding impurity orbitals plays a major role here, right? Though, right, it's kind of, this is still in investigation.
Okay, thank you.
Jan?
Andreas, thanks for the talk. Of course, I know the story very well, but I was intrigued by your statement when you showed the Lagrange surface that you think the fact that the Lagrange integral is equal to 0 is a coincidence. That seems to be a rather new insight of yours. Could you elaborate on that?
Yes. So what is missing from the Fermi surface is exactly one electron, right? And it essentially turns out that in CDMFT, so you can only have a Lagrange surface that actually, so if there's a Lagrange surface, it can only count half of the Brillouin zone volume or the entire Brillouin zone volume or nothing. Okay. And half of the Brillouin zone volume basically corresponds to exactly one electron. So there's actually no other way. And there's no guarantee that if you allow for more momentum dependence of the self-energy that this may not change, right? So you can, right? I mean, you can kind of essentially...
So you say this might be a special artifact of having just two-side cluster treatment.
Precisely, yeah. So, yeah.
Okay, thank you.
André-Marie?
Yeah, thank you for the very nice talk. So, on slide 6, please.
Yes.
So, just a simple question. So these lines between non-Fermi liquid and Fermi liquid, they are crossover lines, right?
Oh, yeah, right. I forgot.
But you have very sharp points. So there are two questions. One is, what is the criterion you use to define these crossover lines? And the second is, can you extract exponents for this, these sort of fans? I mean, it's got crossover exponents, and are they related to anything we know, or?
Right. So first of all, for the crossover lines, I mean, of course, I forgot to mention that. So they are basically extracted from the dynamical susceptibilities, so how they behave. So essentially what we do is we just take the second derivative on the log scale, and what you will actually see is you will basically see two dips when this kind of power law behavior here changes, right? So and that's how we just define it, right? But of course, it's a broad crossover region. Now, as for the v to the, so you mean basically v minus
Right.
vc to some exponent, right?
Right.
So actually for that we would actually have to go a little bit closer to the critical point. So it seems that there is a difference between being somewhat away from the critical point versus very close to the critical point. So there seems to be still some crossover. And it's kind of hard to extract it. So I don't remember the precise exponents, but it seems to be some power law, okay? But I'm sorry, I don't remember the exact exponents, so that yeah.
No problem. Thank you very much. Very nice. Thank you.
Fabian?
Yeah. Hi, Andreas. So on slide 9, you discussed vertex contributions, right?
Yes.
Using your sort of innovative way of approximating them.
So
And you
right.
found that, yeah, slide 9, maybe.
Okay, yeah.
You found that in the Fermi-liquid phase, the vertex corrections become negligible. Now, if I connect your talk to the previous talk, can we sort of make more of this statement? So question A, where does this come from? Does it come from the 3D nature, the filling? Is it general? Question B, can one use your method to make this more rigorous and maybe apply your method in the 2D Hubbard model at low filling and use CDMFT to discuss vertex corrections to resistivity?
Yes. So I would actually be careful with that because, I mean, as I said, we only incorporated the local part, right? And I mean, in principle, I wouldn't exclude that in a Fermi-liquid, things are actually going on a much longer length scale, right? So the surprising thing here is actually that there are these extremely strong local fluctuations that really add quite substantially to the conductivity, right? Which in general you wouldn't expect. So I mean, we investigated actually a little bit. So what we can do, for instance, for the Hubbard model at very high temperatures, right? I mean, there's these measurements on optical lattices, right? And the local contribution doesn't do much there, right? So I mean, so if you assume that the correction to the local contribution is the same for all length scales, actually, then you actually get to a pretty good answer, but it's quite a stretch, right? So there's definitely longer range physics going on.
I see. Thank you.
So Andy says, beautiful talk. He has to leave and we'll come back to you with a question about the vertex corrections. Other than that, we have Antoine again.
Yeah, I mean, actually, my question is also about vertex corrections. So how do you handle, I didn't quite understand how you handle the computation of vertex corrections when the self-energy has so low K resolution. I mean, you basically have 2 K values, right?
Yes.
I mean, in DCA, I mean, I know that's not what you're doing, but in DCA, for example, the self-energy is discontinuous as you cross the patch, and this leads to some headaches with handling the vertex. CDMFT is slightly different.
Right.
But how do you handle that?
Yes, so we didn't even compute the vertex, right? So what we actually computed is we just computed the right maybe here. So what we actually computed is we just computed basically the local current susceptibility, and we just subtracted the bubble contribution from that.
So by local, you mean
so the local thing on the cluster, right? So
okay, I see. Now I understand.
Yeah.
Okay, yes, I see. Thank you.
Henri?
Hello, thank you for this talk. The only point I am somewhat ignorant of all the data on the Heavy-Fermions. So you didn't mention any actual comparison with the experiments. Is there any case where you can do something?
I mean, so we didn't use any quantitative parameters, right? So the model that we used was pretty much a toy model. So where we can say something about it is when it comes to qualitative comparison, right? So to kind of compare universal features. And I mean, for instance, here, I mean, we actually see some nice comparison to the scaling of the optical conductivity, for instance, in ytterbium rhodium to silicon 2, right? But it's of course not quantitative, because the study was not basically done in. So the model that we use is not exactly applicable to ytterbium rhodium to silicon 2, right?
At least do you sketch a situation which is real experimentally, or
Yeah, right. So I mean, this is an actual measurement, right? For instance. So it shows really the same universal scaling, I would say.
Okay.
Or right. And I mean, for instance, also for serum cobalt indium 5, I mean, we can also at least have some. I mean, it's a qualitative handshake, right? So, right. So in some sense, I mean, the resistivity looks very similar, and also we get very similar behavior of the decay rate and the effective mass, right? We checked, so there we also checked a bit, so you can read that in the supplemental material of the PRL. Actually, we kind of checked to what extent our parameter choice is compatible with what you expect for cerium cobalt indium 5, right? And we got some at least reasonable comparison there, I would say. But of course, I mean, a cerium atom is not just a single spinful orbital, right? I mean, it's much more complicated than that. And also the conduction bands in cerium cobalt indium 5 are, I mean, it's all much more complicated than the simple model that we used, right? And in that sense, I mean, it's a totally different computational challenge if you want to actually use make a exact quantitative.
One would like to see at least whether the qualitative effects are represented.
Yeah, right. But I mean, I would say the qualitative effects are there, right? I mean, qualitatively, I would say that this is a reasonable comparison to, I mean, this is experimental data, right? This is our data.
I think this is missing in the seminar, that's all.
Okay. So, okay, yeah. Right. I mean, so the most of the universal features of the strange metal is we kind of see. Okay.